Greetings, everyone. My name is Jacob Hudis. Today, I'm delighted to share with you my dissertation defense talk for my PhD in physics.
Professor Schlockman, Professor Virginia Juan. Oh, so Jorge is going to be on.
The most important part is the actual exam, which starts after the presentation.
Yeah, being the bone steel, but we decided he's too nasty, so we decided to wait for you. All right. Okay. Well, welcome to the dissertation defense of Jacob Hudis. So Jacob joined my group, my gosh, 6 years ago now. So he spent the first couple of years learning various experimental techniques, including ultra-low temperature cryogenics and nanofabrication. Those are very important skills. And also exploring a couple of different projects. But in the end, he found his own passion in superconducting loops. So with a lot of hard work and a lot of directions from Irinel, I think he's done a very nice experiment and found some very interesting results, and also came up with a very robust explanation for the results. And that's what he's going to tell us today in his presentation. So most of us know the scheme, but let me just repeat. Jacob is going to give a presentation. Feel free to ask clarification questions, and then we'll open the floor to the public to ask any questions. And after that, the committee will have a closed session. So, Jacob.
Welcome, everyone. Today, I'll be discussing the research project I've been working on for the past 4.5 years. The title of my talk is Persistent Current Dynamics in Asymmetric Superconducting Nanorings. Here's an outline of the talk. A superconductor is a metal that has unique and interesting properties when cooled to extremely low temperatures. Below the superconducting critical temperature, there is a phase change of electrons near the Fermi surface. 10 to the third, or 1 out of every 1,000 of the electrons near the Fermi surface, change phase to form a superconducting condensate. To help understand this, it's useful to think about the phase change that occurs when water changes to ice as it's cooled below its critical temperature of 32 degrees Fahrenheit, or in scientific terms, 273 Kelvin. This is a phase change from liquid water to ice. In superconducting materials, a fraction of the electrons near the Fermi surface form so-called Cooper pairs, and all of the Cooper pair electrons will join the same quantum state and can be described by a single quantum mechanical wave function. The properties of that wave function dictate macroscopic properties of the material. One example of this is the resistance drops to 0 below a critical temperature. That's what I have depicted in the cartoon to the left. As the temperature decreases, once you get to a certain critical temperature, the resistance of a superconductor drops to 0. Another prominent feature of superconductors is that if you take a thin superconductor and form it into a loop, the flux through the loop will be quantized in units of flux quantum, approximately 2.07 times 10 to the negative 15 Webers. This diagram here shows a thin superconducting loop, and the flux through this sort of loop must be quantized in units of these flux quantum. This picture here shows how superconductivity can be destroyed. Just like the water-ice phase transformation can be destroyed with temperature, the superconducting phase transformation can be destroyed with temperature. It can also be destroyed with magnetic field and critical current. That's what this picture here shows. If you apply too much current through a superconductor, the superconducting phase disappears and it's no longer a superconductor. If you increase the temperature beyond a certain critical temperature, the superconductor disappears and it's no longer a superconductor. And if you apply a strong magnetic field on the superconductor, the superconducting phase disappears. These are three ways you can destroy superconductivity. Why are we interested in superconducting electronics? There's a pressing need for alternatives to conventional electronics, which are faster and consume less power. Superconducting electronic devices have low noise, low dissipation, high speed, and high frequency. More importantly, superconductors are quantum states with macroscopic phase coherence. This allows for new application and technologies not accessible to conventional semiconductor electronics. I want to briefly show some research in the area of superconducting electronics without providing any detailed explanations. The majority of this talk will be devoted to understanding several principles and ideas employed in these devices. There's a lot of research in superconducting electronics. It's a large area in physics. The picture on the left is a device that was fabricated and tested at the Lincoln Laboratory at MIT. This is a single flux quantum integrated circuit. The circuit is made out of superconducting material and only works at temperatures close to absolute zero. In the integrated circuit, quantized units of magnetic flux are used to store information. On the right are 3 nanosquid. The one on the top is one that I fabricated in my first year at FSU. The picture was taken with an electron microscope. I used an electron microscope extensively during my time at FSU, and it is a technology that I find fascinating and incredibly useful. The 2 pictures on the lower left were made at the Institute of Physics in Beijing, China, where I spent 4 months doing research while I was here at FSU. These are devices that measure small magnetic fields. All of these devices have loops in them. When you take superconductors and form loops with them, there are interesting phenomena that can be used to create new technology.
Hello, I'm Dr. Jacob Hudis. If you need math or physics tutoring, please go to my website, acephysics.org, and book a lesson.
There are already some commercial applications of superconducting electronics. A good example of this is a squid magnetometer that uses a squid or superconducting quantum interference device to measure magnetic properties of materials. These are very common in material science and condensed matter physics research centers. On the right are some pictures that show where superconductors are already well established in our society for creating high magnetic fields. There are many examples of this, but the most common is the MRI, or magnetic resonance imaging machine. This is not an example of superconducting electronics, but it shows that superconductors are already integrated into our science and technology and society. I want to briefly discuss quantum computing. It is only tangentially related to my research, but it's one of the most discussed and exciting areas in superconducting electronics, and it has a lot of potential to provide exciting breakthroughs in the next era of physics. A superconducting computer is still in developmental phase. The picture in the center is a flux qubit, also called the persistent current qubit. This is a truly macroscopic quantum object where circulating current can be in a true macroscopic quantum superposition of circulating clockwise and counterclockwise at the same time. The goal is to create a computer where qubits replace the transistor and create a computer that has many more and powerful computational abilities than our conventional CMOS transistor technology. On the left is the Google quantum computing chip with 9 qubits on it. Those qubits are probably not the same as the one in the center. On the far right is a picture of the IBM quantum computer that I found online. The electronics are all at the bottom. This exciting looking machine here is what is known as a dilution refrigerator. I devoted a significant amount of effort to working with dilution refrigerators in my first 2.5 years at FSU. I gained valuable hands-on experience in Peng's lab, and I am sincerely grateful for that opportunity. An unexpected helium issue arose. I was fortunate that Irinel allowed me to conduct measurements at the National High Magnetic Field Laboratory utilizing his advanced dilution refrigerator.
Acephysics.org.
Tutoring with Dr. H. Magnetic flux through a macroscopic superconducting loop. Here's a superconducting loop, and I'm telling you that flux is quantized through the loop. Flux comes in units of flux quantum, which are 2.07 times 10 to the 15 Webers. Let's assume that there's a solenoid. Let's assume that there's a solenoid below the loop, and this is actually how our experiment is done. There will be an applied magnetic flux through the loop. Recall, magnetic flux is B times A times cosine of some angle. The solenoid produces a continuous magnetic field that can be tuned to anything you choose. If the applied flux is not equal to an integer number of flux quantum, then something has to happen. What happens is that a persistent current appears. What happens is that a persistent current appears, causing the flux through the loop to be quantized. The flux through the loop is equal to the applied flux plus LIS, where this is the flux from the persistent current, L is the inductance, and IS is the persistent supercurrent. By the way, this looks like Faraday's law, but it's quite different. You can apply a flux through the loop while it's a normal metal and lower the temperature below the critical temperature, and persistent current will still develop to maintain flux quantization and wave function continuity. There was never a change in magnetic field. This clearly demonstrates a notable divergence from Faraday's law.
All right. Well, okay. So how is it that you can get an applied flux, you can get a quantized flux if you're applying a continuous magnetic field? And so this picture is very important. So on this picture, there's persistent current. This tells you the persistent current as a function of applied flux through the loop. Let's take a look. We'll toggle back and forth between these two. So everywhere along this line, the flux through the loop is 0 flux quantum. Everywhere along this line, the flux through the loop is 1 flux quantum. So let's take a look at this point right here. So this point here says the applied flux through the loop is about 0.75 flux quantum. And but it has to be quantized in units of 1. And so what happens is you'll get a persistent current which will flow, and the persistent current is going to produce another magnetic field which produces a flux through the loop, which would be 0.25 flux quantum, and then you'd have 1 flux quantum going through the loop. Now, if you move up to this location here, the magnetic flux through the loop would be 1.25 flux quantum, which is larger than 1. And so a persistent current would have to come into the loop. This quantized current has to come into the loop in order to maintain the wave function continuity and also to maintain flux through the loop. So, okay, so I wonder if I might actually even show something on the screen here. All right, so I don't know if people can see this on the screen, but so if we have, let's say that there is a 1.5 flux quantum of applied flux going through this loop, then you have two options. There can be a persistent current going this way, which would make this 1 phi naught, the persistent current of minus 0.5 phi naught. When I say the current is in units of flux quantum, what I'm saying is there's a current, and that current would produce a flux quantum of minus 0.5 phi naught through the loop, and then you get 1, or you could have 1.5 phi naught, and the system could choose to have the same energy, 0.5 phi naught in the loop, and then you would have 2 flux quanta. So the system chooses a certain unit of current to go into the loop in order to keep things quantized and to minimize energy of the system. And this, I want to give you some physical understanding of why it is that this persistent current happens. So in this picture here, this is a cartoon of a superconducting nanoring, and it has a magnetic field going through it, which produces 5 flux quantum. Now, there's a macroscopic wave function, which comes from the Ginzburg-Landau theory, that you can work out this, and this just ends up being a particle in a box with periodic boundary conditions because it's a simple one-dimensional loop. And so I think that the best way to visualize this wave function is to cut the loop at one location. So I'm going to call A and B the same location in space. You cut the loop and then you unravel it. And now you can see the wave function is a complex number at each point in space. Quantum mechanics assigns a complex number at each point in space and tells how it varies with how its amplitude and phase varies. And so the phase winds around the loop, and the phase at A and B have to be the same because you have to have
the Bohr-Sommerfeld quantization, it has to be such that, that this is phase coherent. And so you're getting the properties from macroscopic quantum wave function. Okay, so if you were to have 10 flux quantum going through the loop, then you'd have a winding number of 10, and the wave function would wind 10 times a 20 pi rotation. And if you had 4 flux quantum going through the loop, then the wave function would have a winding number of 4, and you'd be in a higher energy state if you have 10 flux quantum. That's a higher energy state of the superconducting condensate. Now, what would happen if you were to put 2.8 flux quantum through the loop? Well, 2.8 flux quantum going through the loop would leave a jump discontinuity in the wave function. And that's not allowed. The wave function must be continuous. And so because it must be continuous, there's something called a current phase relationship. You get a current to flow. The current flows in the opposite direction of the magnetic vector potential. And I drew it on the inside because the current flows on the inside edge, but these are going to be very small devices. And so that current is this persistent current that we're talking about. This is a physical explanation of that. And this is the same picture. All right, so there's this persistent current. And how do you measure this persistent current? So this current, there's this current which oscillates back and forth as a function of applied flux thread in the loop. How do you show you an example of how you measure it? So let's say that we have a loop, and this is a symmetric superconducting loop. So now let's say that we apply 20 microamps to the loop. And I'm just telling you that 10 microamps, I'm going to define a situation where if 10 microamps goes through either the top or the bottom, the loop becomes a normal metal. So you send in 20 microamps, it splits up to 10 on top and bottom, and this is defined to be the critical current for the loop, because I'm telling you, if you have 10 microamps on top or bottom, that's the critical current. And so that's this location. This is a critical current curve. On the right is a critical current curve, and the location 20 is right here. Now let's say that we put a magnetic field through the loop. Well, if you put a magnetic field through the loop, you're going to get a persistent current. So I'm assuming, let's just say that when we put this magnetic field through the loop, the persistent current is 1 microamp. That's a very reasonable number. And so now that the persistent current is 1 microamp, now you're going to, if you were to send in 18 microamps into the symmetric loop, 9 go on bottom and 9 go on top. And then you need to add the persistent current to the critical current. That's our model. Our model is just, we have this persistent current and we're going to add it to the bias current, not the critical current, the bias current being sent in. But now the critical current has decreased from 20 to 18 because now the bottom is 10 microamps. Oh, now the bottom is 10 microamps, and that's what is needed to make this thing go normal. Now, if you were to put a magnetic field through the loop of a different value, and now the critical current is going the other direction. So at this point here, now the top of the loop would become normal at this location. And so the critical current would be this oscillating function that we see on the right. And this critical current, its oscillation like this is how we measure the persistent current. That's the measurement technique. Okay, so this was the first experiment ever was in 1962. This was done by Little and Parks. And what they did, their data is on the left here. This was their data. They did not have a picture of their device. They explained their device. What they said they did with their device, they said they basically took like 2 chopsticks and put a piece of glue, some GE glue is what they called it, and they pulled them apart. And they had to do this many times until they got a very thin wire of this glue. The circumference was a micrometer. And then they cut it into a very small, so they cut off the top and the bottom, so they have a very small cylinder. They deposited metal all over the cylinder, and then they measured the voltage between the top and bottom of the cylinder. And what they found was that the resistance oscillates like this, and it oscillates exactly with the period of the flux quantum. So this is the persistent current that I showed on the other slide. It's the current as a function of flux threading this very tiny cylinder. And if you were to square this function, then you get the below function here. And so it's this set of parabolas that oscillate with flux threading the loop, and they're periodic in flux quantum. And this graph here is what was measured. We're going to jump ahead to 2019. So now we're in 2019. We're 2 years ago. This was a research project by Wolfgang Wernstoffer. And what they did, they took a symmetric aluminum
nanowire squid. So this is made out of aluminum. This white line here is 500 nanometers. The junctions are much larger than the coherence lengths. The junctions are 300 nanometers. And then what they did is they applied magnetic field and measured critical current. And all of these lines are for different temperatures. So it starts out, I guess, 1.5, 1.4 Kelvin, 1.3, 1.2, all the way up to 0.2 Kelvin. So each one of these is a different set of data. And as you can see, their critical current oscillates. It's linear. The line segments are linear, which means because it's a nanowire squid, like the one that I'm looking at. As the temperature decreases, you can see that the amplitude increases. And they also get some multi-valued, there's a little bit of multi-valuedness in the distribution. Now, one important thing that I want to point out is this device had no design geometric asymmetry. They were not studying asymmetry whatsoever. They wanted this to be a perfectly symmetric device. And they made a big point in their paper of saying that these two branches were asymmetric, and that was an unexpected result. And they could only speculate as to why, and their speculation was non-symmetric cooling. But okay, so this is an example of these critical current curves from a group in 2017. Now, let's go to, that was the other one, 2019. We're going now to 2017, where a group at the University of Illinois, Andrew Murphy was the graduate student, and he was really nice. I spoke to him several times. There's his advisor. So they made a asymmetric nanowire squid, but it was uncontrolled asymmetry. By the way, this was actually done with a current pulsed measurement, which we're going to discuss. Every other measurement for all the other data was just done with a constant sinusoidal current source. But so if you look, here's the data right here, and there are multi-valued branches. If you see, there's two branches. That's because they sent in a positive current and a negative current. So when they sent in a positive current would be current going through this way, and a negative current would be current going in the other direction. And here's their data. They superimposed the red lines here. I don't know why they did this. They superimposed the bottom data on the top. So they're just trying to say that it's not symmetric. Top and bottom is not symmetric. So I think we can ignore the red lines because I couldn't just take them out as their data. I wouldn't know how to do that. But the black lines are the top data. And you can see one thing I want to point out is that they mentioned also is that this is a bimodal, actually more than a bimodal distribution. There are two or more distinct switching currents. So if you're at a given magnetic field, you can get a switching current at this point or at this point or here. There's one magnetic field has multiple switching currents. So we're staying in 2017. And so here is an intentional design asymmetry. So in this loop here, they designed this loop to be intentionally asymmetric. There was, it's longer on the top than on the bottom. Their picture is kind of suggesting the asymmetry is in width, but that's not the asymmetry they're talking about. There's a length asymmetry, which means one side is longer than the other. And this is their critical current data, the critical currents at different magnetic fields, and it's highly asymmetric. They were expecting a critical current jump that was not seen. And ultimately, this paper ended saying, we still have questions. There's theoretical questions about how the asymmetry works in a loop like this. What are we trying to do with my research? Well, we want to fabricate devices with well-defined and varying degrees of asymmetry, investigate and understand how the persistent current dynamics evolve with change in. In order to do this research project, we need to make a model for the critical current and then compare that model and then fabricate devices, put them in a dilution refrigerator, bring them to temperatures very close to absolute zero, send in current pulses, and then compare the experimental values to the predicted model. Now, so very briefly, I want to talk about kinetic inductance, which is important in superconductors and superconducting electronics. And this was used in our model. So if you have a superconductor, the current in the superconductor can be written, the energy of the current in the superconductor can be written as the top integral here. The first term is an integral over space of 1/2 mu times the magnetic field squared. And the second term is summing up all the kinetic energy of all of the Cooper pairs. And so the first term is called the magnetic energy, and it can be shown that this is 1/2 Li squared, where L in this case is the geometric inductance that everybody is familiar with from first year physics. Now, it turns out that for superconductors, this kinetic energy term is important, and this leads to something called kinetic inductance, which is only important in superconductors. And the reason that's the case
is because in a superconductor, if you were to put, when you put an electric field on a superconductor, there's no resistance. And so the Cooper pairs have a constant acceleration. And that constant acceleration, there's inertia. When you accelerate something, there's inertia. And this is what leads to this kinetic inductance. And so this kinetic inductance is proportional to the length over the cross-sectional area. So the whole point of that slide is that if you make these wires very, very thin, very, very incredibly thin, I've made hundreds, maybe 1,000 of these. So the line width sometimes was 30 nanometers, 50 nanometers. We tried to make everything less than 100 nanometers, and they were roughly 40 nanometers thickness of aluminum. And so if you make these very thin wires, then when you send bias current in, the bias current divides up asymmetrically. So more current. So if we take a look at the top left, if I send a bias current in, the bias current will split up at the node and more will go through the bottom than through the top because the bottom is shorter. The path is shorter and it's dominated by kinetic inductance if these are very thin wires. And so this is what we need for our model. Now, if you go to the to this diagram here on the right. So now in this case, the asymmetry is a little smaller. On the far upper left has the largest asymmetry. The difference between the length of the top and the bottom is the largest in these three pictures. If you go to the right, the asymmetry gets a little smaller, and when you send bias current in, it still splits up asymmetrically, but there won't be quite as big of a difference between the current. There will be more current that goes on the bottom than goes on the top, but the difference won't be as dramatic as the case on the left. And then finally, on the bottom, you have a symmetric loop. And so the symmetric loop, whatever bias current you send in, there's an equal current that goes over the top and over the bottom.
Acephysics.org, Math and Physics Tutoring with Dr. Hudis.
Using these ideas of kinetic inductance, as well as persistent current and building on work from Nikolov and others at the Russian Academy of Science, we derived these two equations for critical current for loops of any asymmetry in length or width. So I spent a summer deriving these two equations and about a year during fabrication thinking about them, plotting these equations for different alphas and discussing what the solutions would mean. So these two equations are our predictive theoretical model for the critical current of any asymmetry. And there's two types of asymmetry. You can have a length asymmetry. So a length asymmetry, if you look on the upper left, this has a negative length asymmetry because the top length, which is the black part, and the bottom length is the lighter color part, the top is shorter than the bottom. And so alpha is the length asymmetry parameter, and that's length of the top minus length of the bottom divided by the total length. And then there's also an alpha prime asymmetry parameter. So if you look at the bottom left, this has both a length asymmetry and also a width asymmetry because the top is wider than the bottom. And so now we can fabricate any device and measure its alpha and alpha prime, or we can design that into the fabrication process, plug those values into these critical current equations, and then go and put the device in the dilution refrigerator, bring it down to temperatures close to absolute zero, send in current and make the measurements and compare how our measurements stack up against the theoretical values, the theoretical model. After spending roughly one year reading numerous papers on closely related research from various groups throughout the world and completing the theoretical model of critical current, the next step was to fabricate the devices that will be used to test the theory. It took over 6 months to get devices that we were happy with. It was stressful because there were previously undiagnosed problems with the SEM that surfaced when attempting to make devices with line widths of less than 60 nanometers. This picture right here shows the SEM I used, and this is the machine that caused me some stress during my PhD. So to start with, I took a silicon wafer and thoroughly cleaned it, and then covered it with PMMA in an isopropanol solution. PMMA, or polymethyl methylcrylate, is a long-chain polymer commonly used in electron beam lithography. The wafer is baked on a hot plate to remove the isopropanol and then inserted into the SEM where a focused beam of electrons is directed into the annulus of the ring. Clearly, this is not drawn to scale. These are very, very tiny devices. You can't see them with your eye. So the beam of electrons would be directed into this annulus, in this very small area, and it breaks up the PMMA. It chops it up. Next, you develop it, and that removes the PMMA that was chopped up by the electron beam without affecting the rest of the PMMA. And so all the PMMA is still there, except for this very small area that's been removed in the development process. And finally, an ultra-thin layer of aluminum is deposited using a thermal metal evaporator. So here are some of the devices that were measured. All the devices on this slide were fabricated on the same silicon wafer. We wanted all the devices to be as similar as possible, with the exception of the length asymmetry parameter alpha, where alpha is the length of the top minus the length of the bottom divided by the perimeter. So you would take the length of the top, for example, for this one, minus the length of the bottom divided by the total length. And this bottom device has 4 loops on it. Device 5 gave the most interesting data. It had the largest area, and it was measured at the lowest temperature of 250 millikelvin, 0.25 Kelvin. After this device was measured, an issue occurred with the magnetic field coil, and other measurements were delayed for about 6 months. So now that the devices were fabricated, the next step was to take these devices, like I've said, and put them into a helium-3, helium-4 dilution refrigerator, bring them down to temperatures very near absolute zero, and probe the devices with current. And so for a successful research project, we need to obtain experimental critical current data and compare that with our theoretical model. All right, so here's the measurement scheme that we used. It was a ramped current pulse measurement. And the measurement setup sends a train of current pulses into the loop. So let me switch to the spotlight here. And so here are these current pulses, and there's a train of them which is sent into the loop. If the current pulse is less than the critical current, then the loop remains superconducting and no voltage is detected. So current would be sent in here, voltage is measured at this location, and if the current is less than the critical current, the loop is still superconducting and there's no voltage that would be measured across the loop. So when that happens, if there is no voltage, which would happen for the first current pulse we sent in, because we always would send in the current pulse starting from a value much lower than what we would expect the critical current to be, then we'd wait 100 microseconds and increase the current by 7 nanoamps, which is a very small amount, and then send in another current pulse. And eventually the critical current would be reached. And once the critical current is reached, then that current and that voltage value is sent to a database and recorded. And the process was repeated 5,000 times for each magnetic field. So we would send in a current pulse, get one IV value. I mean, we'd send in a current pulse train. Once we find the correct critical current, we'd record that value and then redo the process. And we would do that 5,000 times. And then we would move to the next magnetic field and do it 5,000 times again, and continue this until we go through the entire set of magnetic field values. One measurement took roughly 5 hours. Measuring one device took roughly 5 hours. Device 5 was very interesting. I should mention that experimental physics comes with the messy reality of subtle equipment problems. And like I had already said, device 5 was the device where we were able to achieve the lowest temperature and a magnetic field range that allowed for multiple periods of flux quantum threading. Devices measured before device 5 achieved the low base temperature of 250 millikelvin, but unintended experimental constraints were such that we didn't get multiple flux quantum threading. This slide shows histogram data for device 5. The histogram clearly shows 2 switching current branches, one below about 52 microamps and one above 52 microamps. The lower branch histogram is generally significantly sharper than the top one. On this slide, so on the left, there are two sets of switching current data, one at 0.17 flux quantum threading and the other at 0.59 flux quantum threading. So this is two sets of data at different magnetic fields threading the loop. Each histogram plot was created by 500 current pulses, and I fit the data to a Gaussian plot and plotted the peaks on the graph to the right. So to reiterate, there's 5,000 points here, 5,000 current points here, and there's 5,000 current points here. And for a given magnetic field, I fit the data to a Gaussian. I took the peak of the Gaussian, so this would be at 0.17 phi naught. So if you go, here's about 0.17 phi naught roughly, and this would be the peak of the lower histogram, which would be here, and this would be the peak of the higher histogram. And then if you increase the magnetic field threading through the loop, the histograms shifted. And so here would be 0.59 flux quantum threading, and there'd be a point here and here. And clearly you can see that there's two branches for these oscillating critical current curves. What is the physical interpretation? Why are we getting two branches like this? The first important point is that the model parameter alpha were very close to the actual values for every device. This is exciting because it shows that these equations that I worked on for roughly, a year, they're correct. And so when we took these lines and then we fit them and we compared them with our model and extracted the alpha and alpha prime values, and the alpha values that we got were almost identical, within 5% of the actual alpha values. An unexpected result was that we found two switching current branches. And this means that the first current pulse resulted in a persistent flux quantum entering the loop. There are several possibilities to explain how this could happen. The research showed that it did happen. Our papers discuss a couple of the reasons as to why it happens, as to why it could happen, and there's a little more theoretical work that needs to be done to pinpoint exactly which one of those is correct. But so what's happening is current is sent into the loop, and the first current pulse comes into the loop, and once you get a voltage, it's not causing the loop to become normal. It's not destroying the superconductivity. What's happening is a flux quantum, a persistent current, will jump into the loop. So imagine, let's just say we look right here. Let's say we go to 0.59 flux quantum threading. So then we send in a current, and that looks like it's somewhere around, 48 microamps. Once it hits 48 microamps, we get a voltage, but that voltage is not a result of the loop becoming normal. It's a result of a current, a circulating current that comes into the loop. It's a flux quantum that enters the loop in the form of a circulating current, and that current will stay there forever as long as superconductivity is not destroyed. And so then when the next current pulse comes in, it's going to be at a higher value, and the next current pulse is going to, so first we'll send in a current, we'll get a current of, around 48 microamps if we're right here, get a voltage, but that voltage corresponds to the circulating current flux quantum jumping into the loop. And then the next current pulse, because we send in 5,000 of them, so the next one in the line would come in, and it would give us a higher switching current. And it's a higher switching current because there's this persistent current flux quantum that is in the loop. And at that point, superconductivity is destroyed. And we did a nearest neighbor calculation, and we found that, so first, if the current is a small value, almost all of the time, the next current pulse is going to be higher. And so it's very exciting. And so in general, when the critical current of a squid is reached, the superconductivity is destroyed. By definition, the critical current and all the persistent current must be destroyed. For an asymmetric device, current below so we have found that for an asymmetric device, A current below the critical current produces a phase slip voltage as a result of persistent current flux quantum entering the loop. Now, the next slide shows IV curves from a similar device with very similar asymmetry. And as you can see, these IV curves have a plateau right in the center. And this voltage plateau in the center is a signature of persistent current flux quantum entering the loop. And here was device 4. And so this data was not published because we were focusing on single devices. There's something very interesting about device 4. And so we get 1, 2, 3, 4 voltage plateaus. So this device has 1 voltage plateau, 2 voltage plateaus, 3 voltage plateaus, 4 voltage plateaus, which is corresponding. So first, a circulating current would jump into one of the loops, and then the next. We don't know the order, and then the next, and then the next. And we got many of these curves, and they were all consistent. Here were some of the curves at different magnetic fields, a little bit hard to see, but the curves would be shifted over as expected, but they're shifted over with the 4 voltage plateaus. So this is further corroborating evidence showing that we are getting these quantized flux quantum entering the loop for these asymmetric devices. These two devices were measured about 8 months after device 5 because there was equipment problem and we needed to, there had to be work had to be done on the dilution refrigerator. The base temperature of the dilution the base temperature of the dilution refrigerator was about double that of device 5. Yet it was still significantly lower than the 1.5 Kelvin critical temperature. For this reason, these devices did not have multi-valued switching currents. However, the model still worked. The model provided alphas that were very similar to the actual values for these two devices. And so this is conclusive evidence that the critical current equations are correct. Finally, I want to briefly discuss some results from the very beginning of the experimental portion of this research project. We measured several devices and got confounding results. Later, we discovered that the magnetic field coil was not properly calibrated. We only measured the critical current for a fraction of a period, and therefore the data was not published. However, we obtained multiple switching current branches. As the asymmetry increased, so did the number of branches. Device 1, shown on this slide, produced 13 critical current branches. The critical current branches were separated by 2 or 4 microamps. It was only measured over a period of about 0.3 flux quantum, or a third of a period. However, the results are interesting and certainly warrant further investigation. Device 2 had a larger asymmetry and it had less critical current branches. It's still at 5 and it's expected to have less based on our theory. Summary and outlook. This dissertation examined the effects of asymmetry on superconducting nanowire squids. Our results provided compelling experimental evidence for asymmetry-induced coreless vortices nucleating the superconducting loops. Our experimental results agreed with the theoretical model of critical current. This is conclusive evidence that the theoretical model that I worked on for many months is correct. Our results have fundamental and practical implications on various superconducting electronic devices from squids to qubits.
Okay, thank you, Jacob. So we now open to the general public for any questions you might have. Any questions?
Yeah, I have a question. So,
Jinjiao, you can ask questions now or later in the closed session, but it's completely up to you.
So this question is very general.
Okay.
So currently, quantum computing is very hard. And your technique is to quantum computing?
Jacob,
Can you repeat the
can
question?
you repeat the question?
Yeah, okay. So yeah, Peng, maybe you have to hit mute constantly, Peng, on your thing. Okay, so the question was, could you say it again?
Quantum computing is a hot topic right now. So can your research be linked to quantum computing or applied to quantum computing?
Okay, so the question is, can my research be applied to quantum computing? From what I've done, to be a quantum computer, you need to be in a superposition of multiple states, and that's not part of what I'm doing. But I think this device is very interesting. You never know what someone might come with in the future, but no, I would say there's nothing that I've done is related really directly to quantum computing in that way.
But it may have some relevance.
It may have some relevance, but someone else would have to develop how you.
Asymmetry.
Yeah, the effect of asymmetry could definitely have some relevance.
So any other questions from the general audience? Comments? Once? Twice? If no further questions from the public, then the committee will have a closed session.
I guess that means everyone on Zoom has to get out.
Yeah, they need to log out.
Hello, I'm Dr. Jacob Hudis. If you need math or physics tutoring, please go to my website, asephysics.org, and book a lesson.